Hello. In this video, we're going to talk about surface area. So we're already familiar with this notion that we have some curve and maybe we spin it around the x-axis and it creates some kind of three-dimensional figure. My picture there is very poor. I'm going to draw a better one in just a second. So we're used to creating a solid of revolution, and something that you saw a while ago is how to find the volume using calculus. So what we're going to do instead is we're going to ask ourselves, how can we find the surface area, the lateral surface area? So here's kind of our setup. Let's imagine here is the x-axis, and I have some graph like so. And let's suppose it starts at x equals a and ends at x equals b. And let's imagine that we spin this around the x-axis. So I'll try to create something with symmetry. And so we get this tube-like thing. Right, so hopefully you're imagining this as three-dimensional object. So we want to know, what is the lateral surface area? What is the surface area of all this stuff? We're ignoring this disk at the edge and this disk at the edge, just the stuff around the sides, the stuff that's actually created by the green stuff. How do we find its surface area? So what we're going to do here, I'm not going to give you the whole proof, but we're going to think about how could we approximate this. So many of these problems come down to, what's a good way of approximating this? Can we run a limit on that? Does it turn it into an integral? So what I'm going to imagine is that we cut this up. And let's suppose we have just sort of a portion right here. Let me change the color. Corresponding to, say, here's like x sub k. So let's imagine we're just taking this portion right here and spinning that around. Right, so we're imagining just that little strip. So what that strip looks like, from a certain point of view, you might say it's a cylinder, right? It's round, and the radius here is actually drawn vertically, right? The radius is how far is it from this to the outer edge, because the roundness happens vertically. And then this is like the height. What we actually have here is, we notice this is a little bit slanted. So the shape we have is actually what's called a frustum, more or less. I'm doing a little bit of approximation. Don't panic about that. A frustum is basically like a cylinder that has slanted edges. You could define it as basically taking a cone and then slicing off the top. But a frustum is essentially a slanted cylinder. Now, the surface area of a cylinder, or the lateral surface area of a cylinder, would be 2 pi times the radius times the height. Right? We've seen that before. And so for this frustum, we're thinking the surface area would be something like, right? I'm going to cheat a little bit here. This all works out in the details. I want you to believe the formula even if we haven't seen a complete proof. For a frustum, the area we think should be 2 pi times the radius. And it's a little bit tricky here because there's a different radius at the bottom than at the top. Right, so I'm going to put that in quotes, like some radius, something measuring the radius, although it's a little bit complicated. And then we're going to multiply that by essentially the slant height. This is not literally a height. What's playing the role of height actually is diagonal. So I'm putting that in quotes. So it's kind of like a cylinder, but we're realizing there isn't exactly one radius. And the quote-unquote height is not the vertical height, it's actually how much the slanted diagonal there. So this is kind of what I have here. For a cylinder, our area is 2 pi times the radius times the height. Now, looking back at this graph, here is the graph of y equals f of x. For this cylinder or frustum, however you think about it, what is measuring its radius? Where is the center of that cylinder or frustum? Where is the edge? And how far apart are they? What is measuring that? Hopefully what you're realizing here is that this radius is basically measured by how tall the graph is. This is kind of similar to when we did disk method. Right? The height of the function very often represented the radius of the disk. So the radius is basically f of x, right? Maybe f of xk if we're imagining breaking this up. And then the height, again, is some kind of slant height. Going back to the diagram, the height is actually this thing here. And really, if we zoomed in, we would realize this isn't even a frustum because this presumably has a little bit of curve to it. In a frustum, it's a straight diagonal. This has some curve to it. So our feeling is that this thing that's like the height on the edge is something like arc length. Right? The quote-unquote slant height here is basically measuring how far along that original curve do I travel. So I'm skipping all the details, but what I want you to realize is that the area of each of these strips basically comes down to 2 pi times r, and r is the value of the function at that point, times something kind of like arc length. This is our modification of that cylinder formula. 2 times pi times the value of the function, times something that kind of measures that arc length. We could add these together, we could run a limit, we could do some tricks. I'm hiding all of that stuff because it's unnecessarily complicated for this particular example. But hopefully this kind of makes sense, right? It's 2 pi times r times h. And we realize that the radius is measured by how tall the function is. And the quote-unquote height of each one of these cylinders or frustums is actually how much arc length do we have on the side. When we put all this together, it turns into this integral. Right? So there's some magic behind the scenes, but this is what we're seeing. We're seeing 2 pi times the function value, which is measuring the radius. And then this is exactly the thing that we integrate to find arc length. So it's not shocking that we see that here. You are going to have to just learn this as its own formula. It's believable why this is the correct formula, but I haven't really proved it. So this is how we find the lateral surface area when we revolve y equals f of x about the x-axis. As usual, we could have our perspective flipped. Maybe x is a function of y, and we're spinning around the y-axis. So it would look like this. I'm really just interchanging the role of x and y. So at the end of the day, this is just a formula to know. Hopefully you have some idea of why it's plausible, even though we're not going through all those details. Let's just do a couple of practice problems. So let's imagine we have the portion of y equals x to the third from 0 to 1. Something like so. And let's imagine that I revolve that about the x-axis. So maybe you can imagine, what does this look like? It's going to be really long and thin, but kind of dimpled, right? A little bit like a symbol, right? This kind of symbol, not S-Y-M-B-O-L. Right? So maybe you can imagine this, maybe you can't. But we're trying to figure out what is the surface area that we create. All right, well, here is our formula. We need to know f of x, we need to know f prime of x, and then we'll just see what integral we have. So for this example, f of x is x cubed. So f prime of x is 3x squared. So our surface area is the definite integral from 0 to 1 of 2 pi times f of x times this thing we recognize from arc length calculations. And this one we can actually do without a calculator. So let's notice we have the integral from 0 to 1 of 2 pi times x to the third. And then we have 1 plus 9x to the fourth. This would actually work as u substitution. So we'll notice if u equals 1 plus 9x to the fourth, then du dx is 36x squared, x cubed, sorry, which would cancel with that x cubed. I'm not going to do the full u substitution. I'm going to try to do this intuitively with a little bit of guess and revise. Oops. So my antiderivative here, I have this thing to the 1/2 power. So I know when I take the integral of that, it's going to go up to the 3/2 power here, and then we need a 2/3 to cancel that. And what I'm noticing is by the chain rule, if I took the derivative of this, 36x cubed would pop out. I don't have 36x cubed. I have 2 pi x cubed. So I'd actually have to multiply by 2 pi over 36. Right, so let's just pause and see what would we get if we took the derivative of this thing. I'm going to do this at the side. Right? It really is nice to be able to do some of these without the formal u substitution. I'm just going to check. Right, if y equals 2 pi over 36 times 2/3 times 1 plus 9x to the fourth to the 3/2, then y prime would be, all of this stuff is constants, times 3/2 times 1 plus 9x to the fourth to the 1/2 times 36x cubed. The 36's cancel, the 2/3 cancels the 3/2, and we have what we want. So that is our correct antiderivative. Maybe while I'm here, I'll simplify it. So let's just notice we basically have 4 pi on top, and 36 times 3 is 108 in the bottom. And 4 over 108 actually simplifies to 1 over 27. This gets a little tedious, but it is one of these rare examples where we can do it without a calculator. So that is our antiderivative. So if I plug in 1, I get pi over 27 times 1 plus 9 times 1 to the fourth is just 10. And if I plug in 0, this is 1 plus 0 raised to the 3/2 is just 1. So what we have here is pi over 27 times 10 to the 3/2, which we might write as 10 root 10 minus 1. Maybe not a very easy number to wrap our heads around, but you could plug that in your calculator and get a numerical value. Even if you did, it's very hard for us to guess what this is. I think people have pretty poor intuition about surface area. So you really have to just trust this formula. A little modification here. What would be the integral if we revolve the same portion of the curve around the horizontal line? Wait, why did I put an 8? Sorry. I was thinking of 2, but we're just going from 0 to 1. I apologize. So this picture, right, this is 1. So my scale is all messed up. I really apologize for that. I was imagining x cubed going to 2, 8. But all of this computation is correct. But the picture should have been more like, sorry, let's do this better. We have, here's 1, here's 1, here's negative 1. The graph of x cubed on that interval is like so. So we spin it around. And we get something like this. Right? Maybe you could argue it's horn-shaped. Now, just a little modification. What do you think the integral would be if we revolved the same portion of the curve about the horizontal line y equals 5? So here I'm going to draw a picture. There's my horizontal line, y equals 5. And here is my same portion of the curve. We want to be a little bit flexible. We had this formula here, but it's good if we remember where this comes from. That what this comes from is modifying this area formula from a cylinder, which was essentially 2 pi times the radius times the thing that's kind of like a height. What changes in this problem is simply the radius. So the radius now would be, oops, let me change my color. My radius would be the distance between the curve and y equals 5. So the radius would actually be 5 minus f of x. Right? That f of x from the original formula was just measuring the radius, assuming we're spinning around y equals 0. Here, if we're spinning around y equals 5, we just do top minus bottom, and it's 5 minus x. So the integral we would do here would be the integral still from 0 to 1, still with the 2 pi. The thing playing the role of radius would be 5 minus f of x, and f of x is x cubed in this example. And the length is still the same. The thing measuring the length is the same. I'll just write it with the square derivative squared. So similar, but we have to be a little bit flexible. Here's one for you to try. All right, I'll draw a picture, and then I'll actually pause for you to attempt to do it. So let's suppose we have the portion of y equals x squared from 1, 1 to 2, 4. And let's imagine we revolve this. So notice here, I'm revolving this around the y-axis. That is different from what we saw before. Can you find the resultant surface area? At least set up the integral, even if you don't want to do all the steps quite yet. Hit pause and give this a try. All right, so if we're spinning this around the y-axis, it's going to look something like so. It's going to be kind of like a bowl or a mug without the handle. It's going to look something like so. If we're spinning this around the y-axis, we really want to look at this and say, I don't want to think of this as y as a function of x. I want to think of this as x as a function of y. So that we can do an integral here beginning at y equals 1 and ending at y equals 4. We'll have an integral as y goes from 1 to 4 of 2 pi times the radius. And in this version, this function measures the radius. If we're spinning around an axis, the value of the function measures the radius. So that would be, oops, square root of y. And now let's figure out the derivative. G prime of y is 1/2 y to the negative 1/2, which is 1 over 2 root y. So here we have 1 plus derivative squared. So again, 2 pi times the value of the function times this arc length kind of thing. Now let's clean this up and see if we can actually do it. So I have 2 pi times the square root of y times 1 plus, if I multiply this out, I have 1 over 4y in the bottom. I have 2 square roots, so let's combine them. We're allowed to do that with multiplication and division, not with addition and subtraction. So we have the square root of y times 1 plus 1 over 4y. And if we distribute, we have y plus 1/4. And we can do this without a calculator. My antiderivative here would be y plus 1/4 to the 3/2 with a 2/3 to cancel it and a 2 pi in front. Technically, we need to be thinking about chain rule, but the inner derivative here would just be 1. So we don't have to worry about that. If you took the derivative of this, the 3/2 cancels the 2/3, the new power is 1/2, and this is just hanging out. So if we plug in 4, we get 2 pi times 2/3 of 4 plus 1/4 to the 3/2 minus 2 pi times 2/3, 1 plus 1/4 to the 3/2. This is not going to be a pretty number, but it is one we can get without a calculator. 2 pi times 2/3 is 4 pi over 3. I'll factor that out of everything. And then this is 17/4 to the 3/2 power minus, this is 5/4 to the 3/2 power. If you really wanted to, we could continue to simplify. This would be 17 to the 3/2 over 4 to the 3/2 minus 5 to the 3/2 over 4 to the 3/2. 4 to the 3/2 is 8. So we can combine those with a common denominator of 8. And we'll remember 3/2 power just means one of them times the square root. And then finally, we notice that the 4 and the 8 would cancel. So if we bring this in front, we actually have pi over 6. This is 4 pi over 3. It would be 4 pi over 24 if we multiply. So this is probably the nicest way to write this, which isn't particularly nice, but it is kind of pleasant to realize we can do this without a calculator. As awkward as the number is, it is an integral you know how to do, and we can plug in and do our best to prove it this way. This is not part of the AP curriculum. I just want you to be aware of it because, maybe you'll need this. This strikes me as something that in engineering and design, you would actually want to know, right? How much surface area does that 3D thing have? Probably a computer is going to do all the work for you anyway, but you need to understand what do we program into the computer. All right, that is it for this video.